All right, we're learning J. I'm nervous because I haven't done a J for a few days. One way of looking at it, it's a great thing because you have to start like cold and get back into it, and that's great practice. You know, like sort of that almost like a spaced repetition kind of idea of like, oh, now that I have to remember this stuff, it's really going to solidify it. On the other hand, I look at it like, man, all the sessions that I missed, you know, that's so many less reps I have under my belt that I could have under my belt. But in any case, it is what it is. I wasn't able to do it for a few days, and you just show up. The point is to show up and make the best of it. So we're going to get right back into reading some J phrases. We looked at bond curve, we looked at rank. Let's look at ambivalent functions, and let's just, seems like this shouldn't be too hard here. Oh, this is a function declaration. That's what this colon means, I think. Base 10 log for monadic case. So this ampersand is the width. Maybe I should make this. Oh, this already is large. I'll make it larger. Oh, perfect. Okay. I should have made it this large the whole time, probably. All right, so this is saying 10 with logarithm. So exponent is the caret. So logarithm is the caret dot. So this dot kind of like indicates to us it's the x, you know, it's not always exactly like this, right? But I think they try to be consistent a lot where they're like, okay, if caret's exponent, let's make caret dot the logarithm since they're like inverses of each other. All right, so what is this telling me? The phrase HFG, H is F code G, so defines H as a function whose monadic case is F and whose dyadic case is G. The components F and G may be functions already defined in or they are tacit explicit phrases. Moreover, either but not both may be defined in terms of the other by using self-reference and a tacit definition. So we have not seen that before, so that's something new to learn. But let's just see if we can read this code. Like I said, I understand this left case. So this is the monadic case of V0. And this is the dyadic case. So basically what we're saying is that this is just normal logarithm, but if you use it monadically, it's 10 with the logarithm, log 10 log, whatever. Now this is saying the same thing, but it's using self-reference to the dyad. So 10 with self-reference. And then, so that gives me, okay, here's the thing that I'm referencing. So we're going to substitute that in where the $co goes. But let's look up $co just to make sure. Sparse shape of self-reference. Okay. And let's get back to that habit of seeing how they call things. Although, you know, I sort of haven't done it because I feel like I'm starting to get the hang of how they call things, but we'll see it here. So if I go to self-reference, they do call it $co. Cool. $co denotes the longest verb that contains it. What does that mean? So here's some more code that we can try to read. I'm not able to read this code. I don't know what this means. The agenda at dot chooses the verb. I don't know what this means. It chooses the verb bracket whatever as long as the argument reduced by 1 each time by the application of the decrement, whereas the decrement is a this is the decrement, okay, as long as it remains non-zero, and when the argument becomes 0, the result of the right argument of at dot is 0, and the constant function 1. So this is kind of like this self-reference. Okay, this is probably going to be important because this seems like maybe how like we define recursive functions. So if, oh man. So if self-reference at, so what is at? I mean, we saw the at sign before. Soon I'm going to get to the point where I'm not even going to look these things up in the dictionary. Oh, a top, of course, a top. I do not know what agenda or at are. I do know what a top is. Where does my self-reference guy go? Here he is. Okay. So self-reference a top of the decrement. So we can read this much, although what this self-reference a top of does exactly, I kind of only superficially get. Whatever. But this is decrement, so it's going to do the self-reference atop of decrement, and I do not know what this agenda means. All right, we'll come back to this because I don't know. So self-reference seems to be important, but in the case of these ambivalent functions here, we just sort of see that this self-reference refers us over to the other case. And this is going to be the same thing using self-reference to the monad, which is, now this is like messed up because now the monad is 10 width. So I don't exactly understand what's going on over here, but I basically get the idea that they're going to have to they have to unbind this. So this is currently, they call it binding, right? Oh, no, I want to be in the phrases. These other phrases. Bonding. Yeah, bound. So this has the logarithm, but it's bound. It's 10 with the logarithm. So here, if they want to use self-reference, they have to actually unbind it. So this is pretty complicated. And I was trying to get away from having to read some of these, but this one's in the phrases, so that's how I'm reading it. So I didn't necessarily, when I saw the self-reference dictionary definition, feel compelled that I fully have to be able to read these examples, although would be great because look, here's quicksort in this line of code. So it would be really cool. We'll get there. But yeah, all right, the struggle is on. Let's do it. So in the prior videos, past few videos, I was really just trying to find one line of code to go ahead and understand. And I think I found it. This is our one line of code. Let's see what we can do. First thing, I'm going to copy this definition into the J interpreter. All right. So the monadic case is easy. It's 10 logarithms. So if I have V, so there's V2. If I have V2 100, it's 2. So 10 log 100 is 2, right? And if I had V2 1, I get 0. V2 0 is some infinite thing or whatever. V2 1000 should be 3. Right. So 10 log 1000 is 3, I guess. 10 log 1000 is 3, which means that 10 exponent 3 is 1000, right? So that's cool. So we have V2. And we understand the monadic case. Now the dyadic case is basically that I can say like 8 V2 64 is 2, right? So now I can use this as a normal, this is just the normal logarithm. So 8 log 64, same thing. So here you see the monadic case and the dyadic case. So basically here we're using self-reference. Here we're using maybe I should make this one bigger too, but then it gets a little hard you can't fit enough code on the screen. Okay. So we're looking at this right side, and how it's using a self-reference to this to to get you this. Okay, so first let's look at this square bracket thing. The left and right square bracket. We'll start with the right square bracket because we'll start with the left square bracket because if we go right to left, that's the one that comes first. Same left and same right. Okay, they both equal same. The monads, they just yield their argument. And there's no difference between these in the monadic case, right? So if I say A is A is the integers, with a shape of 5. There's A. So if I say square bracket A, that's just the identity. And if I say the other square bracket A, it's still just the identity. But if I said 0 square bracket A, I would get 0. Like 0 right bracket. Oh, you know what? That's why we should see what these things are called. That was the whole idea of this. So let's see what they call this thing. Square left, square right. Okay. So if I say 0 square left A, I get A. Wait, square right. It says pointing to the right. So I say 0 square right A, I get A. And if I say 0 square left A, I should get 0. So this is what this does. So these are the identity functions. And I'm sure that can be useful. It seems to be in use here. So we see we do have these parentheses here. Or no. We have these big parentheses. I don't know why the whole thing needs to be like that, but probably it's because we are creating a verb. So this like I think it's one of those cases where if we were able just to write out this code and substitute in things, we wouldn't need the parentheses, but we actually do need to create a verb. It's not an expression. I think that's what these parentheses are about. We have these parentheses here where we're saying 10 rank 0. Obviously related to trying to get rid of something over here, okay? And so here we have the logarithm again. Logarithm atop of the identity. And the identity is going to be, I think, the argument. But I'm not sure. But I think this will be the identity of the argument. So, no, I don't know. All right, so we have a divide. That's divide. And we have self-reference atop of the identity. What does that mean? Wish I had a simpler. What if we go back to our self-reference here? Is this one simpler? I don't even know what this is. This says denotes the longest verb that contains it. Yeah, I don't know what that means. All right, let's go back to our phrases. What are all the verbs we have here? Multiply, divide, logarithm, logarithm, atop, atop, atop. We have a rank conjunctions, 0, and we have the self-reference. So there's not really any complicated verbs in here that I don't understand because it's only just basic math operators here. So this should be like a simpler case we basically have multiply, logarithm, divide, logarithm. There's nothing, complex, except when we bring in this self-reference thing. And we start to wonder also, what is it we're taking the identity of? And we also wonder, okay, when are these things used monadically or dyadically? How does this all apply? And what goes in here? Oh, wow. All right, let's see if there's some way I can break this down in the interpreter. This is definitely, we talk about making my brain struggle. I'm glad that we're finally getting to the point where I just get right into struggling. It's so much more good. But it's kind of sucks too. See, I don't know how I can substitute in things for the self-reference. This is what's definitely going to kill me here. We can start with a known value. So we know that 10 V2 100 is 2. All right. So somehow this section over here needs to get us to the 100, and it uses this. So I don't think this is going to work, but what I'm going to do is take the right side, the dyadic case, and I'm just going to take our self-reference and substitute in 10 with logarithm. Now, I'm not sure that will work. Okay, and let's actually make this a verb. So we'll just call it verb 3 is this. See if this even works, first of all. It does, but if I do 10 V3 100, okay, so this still works. So I was able to take the self-reference, at least in this case. I'm not sure if I'd always be able to do this, but with this line of code, I was able to take the self-reference and just substitute in the verb. And just to make sure it still works, we need to do something that is not with 10. 10 V3 64 is 2, or 8 V3, right? So that's cool. And 2 V3 8 is 3. So it seems to be working. So we've got V3. So we're breaking it down. Now, this becomes a whole single verb. Actually, it took out the parentheses when it showed it to me. I'm not sure. I am very sure that if they showed me these parentheses in here, they probably exist for a reason. If I did this whole thing without the parentheses, maybe it wouldn't work. I mean, we could see that by trying it, but before we do that, that doesn't seem too important at the moment. Let's do something more important. Let's just take this and, so this has got to be dyadic. So I could not just do 2 and then all of this stuff and then 8. That's not going to do anything. Yeah. I mean, it's going to do something, but so in this case, I really probably do need the parentheses. If I wanted to just take it like this and now try it, will that work? Okay. So we've been able to take this out of this monadic dyadic defined verb to simply a dyadic. So we really should have called this D1 instead of V3, but it doesn't matter because this is for verb, and we would have used M for a monadic verb and D for a dyadic verb. But we took it out of the ambivalent function, and now we defined it as a dyadic function, which is cool. And now we've taken it just to a single sentence. So that is cool. But the problem with it is it's kind of easier to do this stuff with monadic verbs. It's like I still need this all wrapped up in here. It still has to be a single verb. So I really haven't taken it out that much. So it's really 2 And basically, all of this evaluates to log somehow. And I don't know how, but let's fucking see. Maybe I can take out some of the tops, but I'm not sure because you really need... Okay, so what happens is with the tops here, I think this identity... Oops. I think this identity gives me 8. I think this is a right identity. Like, I'm sorry. I think this is a... Ooh. This is a left, not a right. What I was going to say was that this would be a... Oh, no. So this is a top. So a top means, I think, that this is a monadic. And although I still wish they would have done right or square right instead of square left. You know what? Let's try this. What if I take all of this and I replace that to make myself feel more comfortable? What if this was right square or square right? It doesn't work. Okay, so if I do right square, it doesn't work. So it's definitely supposed to be... Oh, no! That is right square. I have such a hard time reading this because I look at it. Oh, no. It was left square. I was looking at mine. That was right square. This is square left. Okay. So it needs to be square left. So the fact that it needs to be square left definitely indicates that this is being applied dyadically. And to what is it being applied dyadically? I thought it was being applied to the argument. Okay, yeah, I do not need an identity to stand in for the argument because the argument's just there. It's applied right to left, and the argument is just there. But I don't understand this atop of then. You know? It's pretty tough to read. And again, this is another one of those cases where probably if I were just like a little better at math, I would probably like be putting some more of this together. Atop. Increment atop of minus 7 is 14. Double the negation. Oh, this is double, not increment. So yes. Double the negation. Double atop of negation, 7. So negative 7 doubles negative 14. Okay. This has different forms. This you have u atop v y. This is the monadic form. And here you have the dyadic form. X u atop v y becomes u x v y. So we also need to look at the atops and know if we're using a monadic or dyadic form. But you don't really have to think about it much. Or you do, because it becomes ux. U gets applied to x. Y gets applied to v. The whole thing gets applied to x, but if x is a noun, what does it mean? I don't know. Well, we can look at it here. Okay. So what we're saying is this is going to expand to double 3 atop minus 7. Well, the atop means it's going to say double 3 minus 7, basically. So you have minus 7. Oh, and this is a dyad. Right. So you have this dyadic thing, phrase or whatever, and then you have this monad that it gets applied to, which is double. Okay. Let's go back to our thing. Oh, I'm 25 minutes into struggling on just this one thing, so I'm doing perfect. This is perfect. It's okay if we don't figure this out. If I don't figure this out, it's all right. But I do understand now that this atop can be in a dyadic form which is basically going to say, take what's on the left, pop it in here, so take the identity of the left and apply it to 8. So that means that this, in between these, I'm actually going to be taking whatever was on the left side. So, oh man. Can I try putting some parentheses in here to understand how it's being evaluated? I think this is just kind of a dead end, but just something to do when my brain's working. I sort of feel like, okay, so if this is a dyadic use of a top, well, I guess it's just the dyad. Oh, man, it's right. Let me hold up. So if you go to a top, you have X, U, a top, V, Y. Okay? That's if this is the dyadic form. Well, in this case, what's on the left side? So this is U, and this is V. Y should be 8. So what's X? It's like, well, all of this should be X. But it doesn't work that way in my understanding of how this stuff gets evaluated. But maybe, like, if you did it with these parentheses, then yes, it would work that way. So, also, I can't just have a divide hanging out here. So actually, that's not, like, this wouldn't make sense at all, as far as I know. Right. So that's not our answer. Okay. So those parentheses are not helpful. This times this, it's this divided by this times this. What does this mean? 10 conjugated to 0. What does that mean? 10 conjugated 0. That doesn't mean anything. Man, this is killing me with the atops. The logarithm atop of 10 conjugated to 0, that doesn't mean anything. Well, the struggle is real. It's very anticlimactic, but we're a half hour in and nothing doing. That's the point of this. Oh, I have to get better. It's now that we're getting into these videos that are actually me just going right into practice, that I need to start stating more clearly in the beginning of the videos what I'm doing here, which is practicing to show what it's like to learn a language. So we'll make sure I do that in the next learning session. We'll talk about instant dev career and learning quickly and things like that. But for right now, what we've learned is that I have no idea how this code works. I have a vague idea, but they've introduced this self-reference thing. And it wasn't the point here. I mean, the point here was the ambivalent functions, but ambivalent functions can use self-reference. And so here, self-reference is very easy. I realize you just substitute in this, right? But here, they're substituting in, 10 with logarithm. So I got that, and we got that here. They're substituting in 10 with logarithm. But actually, how does the rest of this work? This entire verb here is actually this like a derived verb or whatever. Or oh, wow. All right, I suck. Let's look at hooks and forks again. Oh my gosh. I don't want to because I don't want the videos to go on too long. And we're at half an hour, but just really quickly, we're going to look at hooks and forks. This appears to be a fork. FYGHY. I mean, just I see this FGH, but it's not really a fork. Actually, it's not a fork because we have this multiply and divide here. This is not a fork. This is just saying evaluate this first. That's all it's saying. Like, is it? I don't know. Because it's basically, it seems to me to have this is some kind of verb train, maybe. I don't know. It must be a verb train because that's how we get like a derived verb. And then we can use this as this derived verb. So it must be. But does it actually expand into a thing like this? Plus y divided by tally of y, or yes, FGH. But this is like a, if that's so, then this is a verb train that's like 1, 2, 3, 4, 5 things long. At least 5 things long. Because you have this, there's this atop of. See, I think it's not a verb train because I think that atop of like is also another way of creating these derived verbs. But I don't understand what's going atop of what. I have no idea when these multiply and divide things factor in. I don't know what this is supposed to. This will do nothing if I just paste it in here. It'll just show it back to me. What if I just did this? You know what? Let's break it down like this. I don't think this will help me at all. But just for exploration purposes, what if I did that? Okay, yeah. What is... I don't know. It just gives me some kind of answer. This is without that self-reference to the 10 with the log. All right, well, that's it. Thank you so much for hanging out and watching while I try to do this. Maybe your brain is just as puzzled as mine. But that's the whole idea. We're definitely triggering the neuroplasticity here. I mean, I'm putting in the effort, which is what all I really care about is that when I do this, I'm putting in effort and I'm seeing things that my brain doesn't get, and so it has to stretch. And so we're certainly stretching here. So my brain's getting warmed up and learning. And yeah, I have complete faith that, you know, sooner or later, I'm going to come back and this is all going to make sense. But if I don't try to stretch my brain, this will never make sense. But if I just go through a little bit of discomfort now, I know one day in the future, I'll be able just to go ahead and articulate this and read this, just like I can with some of these simpler phrases or, you know, code that I've already studied, things like that. I believe I spent a long time trying to articulate this code, and that actually I can do it, right? So it's like just a little quick review to make sure that like I haven't fully forgot how J works. We're going to say 1 with, and this greater than dot. This is just making sure that 1, this is basically greater than dot is going to say, give me the lesser of these two things. So whatever the argument is, I'm going to get the lesser of the argument in 1. So this whole thing is just making sure that my argument is positive. Now, remember, in this form, my argument can be negative or positive. Okay. So make sure that my argument is positive, and I'll either get my argument or 1. And at top of that, say 10 with the logarithm. So this is just going to say 10 log whatever. You know, if it's 10 log 1,000 or 2,000 or however you get to it. And then we're going to say, take the floor of that. So for instance, if I have 10 log 2,000, the answer is going to be 3 point something, right? So this will give me 3 point something, and this symbol less than dot is the floor. So 3 point something, the floor of that is just 3. And then I'm going to increment it by 1, and that's going to tell me that in the number 2,000, there are 4 decimal places. So I can just come back and read this code, you know, and I can even articulate this whole code from left to right or right to left or whatever. So, for instance, increment atop of, the lesser of, atop of, 10 with logarithm, atop of, 1 with the lesser of the argument. So I have no doubt that with work, I will be able to come back and do the same thing for this code. And little by little, we're going to learn how to program J. Or you can use this just as an example for yourself if you're trying to learn Python or JavaScript or Go or Java or C#, whatever it is you want to learn. I don't care. Swahili. You have to struggle. All right. Thanks a lot. I'll see you the next time.